Let's work with integrals. An integral of a function, of course, it will be bounded. It means that it has a boundary between 2 points. This integral, also called sum, is actually the area underneath the curve limited by the curve, the x-axis, and at the same time these two boundaries limited by x0 and xn. Okay, imagine them as two vertical lines cutting through the curve, and this is the area underneath the curve that is actually the value of the integral for that curve. How do we write such program? We need a point that starts from an originating boundary. The second boundary would be xn, the second point for x. Also, you need a step value, and here, by the way, we are using the rectangular method. It means that it is an approximation. Okay, you jump to the curve, then you go at each point, you measure the width for a step, and you multiply it by the height of the first point you encounter here, which is the intersection between the first point and the curve. Okay, then you jump to the next one. Then the next one, where does it intersect? That would be the height of the rectangle. You multiply it by the step. So each time you multiply the height of the first part of the curve where you intersect with this point with the width of the step. As much as you reduce the step size, you would get a more accurate value. But in both cases, the rectangular method is not the most optimal method. The integral will solve for a polynomial function of the second order, means that it is of the form ax2 plus bx plus c. So let's at first declare a function where it will calculate for each value of x the value of y. So double poly equation, we will call it polyec, a double b and c, and the value of x double x. It will return a times pow x2. Why? Because a times x to the power of 2 plus b times x plus c. Then we will declare the function that will calculate or evaluate the integral using the rectangular method. Double integral, double a, double b, c, the constant values for the function. You need the first boundary, which is double, we will call it b1. Then the second boundary for the integral, b2. And finally, we need the step value. Okay, double step. Again, the value of the step, how small it is, it would define the accuracy and the resolution for the integral. Let's declare a variable x that will start in b1, okay, which is the first boundary. Another variable s that will be initialized at 0, that will be the sum. So at each iteration, we will be adding to s in order to obtain the final integral value. While x is less than b2 minus step, that's the reasoning behind that. While x is less than b2, the second boundary, minus step, because the last x should sit here to measure the height. It needs to be not at the last position or the last boundary, but one step behind it, okay, at the last iteration, because at this point we would evaluate the surface area of the last rectangle, and then we would break out of the loop. While x less than b2 minus step, we need to add up s, which is the sum or the integral. So s plus equal to the function polyec a, b, c, and x, which is the value being iterated, surrounded with parentheses, multiplied by the step. Then we need to iterate the step, so x plus equal step. Finally, return s. Let's go to the main function to give an example. So we will evaluate the integral of the function y equal x2. So for y equal x2, you have only a equal to 1, but b and c are 0. So integral of x2, y equal x2 between 0 and 2. And the step value is equal to 0.01 to have a good resolution, a good accuracy. Double sum is equal to integral 1, which is a, and b and c are 0. Then the boundaries are, you see here, double b1 is equal to 0, b2 is equal to 2, 0 and 2. Finally, the step value is 0.001. Printf of x2 between 0 and 2 is percentage f for the sum value, and finally sum. Let's run it. And as you see, we've gotten a pretty good value for y equal x2 integral between 0 and 2, because it is so close to the actual value. The more accurate value would be 2.66666, but it's fairly good for the rectangular method.